Hey y'all. So we're here with the lesson on exponential functions, and what we want to do is we want to introduce you to exponential functions and exponential growth. And then we want to get an idea of what an exponential functions equation looks like and how that relates to the graphs and what kind of characteristics these exponential functions have on their graphs. So in order to do this, I thought we might bring up what's known as a Ponzi scheme because one of the big concerns in today's society is the amount of scheming that's going on, especially where now people can hide behind virtual worlds and such, and con people that aren't as savvy in the virtual world is certainly becoming more of a cyber threat these days for the average person. So what I want to do is talk about what a Ponzi scheme is, how you can recognize one, and then I'm going to show you how it relates to exponential growth. So a Ponzi scheme is basically an investment scheme where you have, let's assume that there's one person at the top. That person basically takes money from the people directly below them. So um, they would recruit, say, two people, and they would, for example, say, listen, if you give me $1,000 today, I'm going to turn around in a week, I'm going to give you back $2,000. But the catch is those two people now have to go and recruit two more people. And so what you have is this system where money is essentially funneled up from new investors, all right? And it's not actually any investing going on. There's just literally money funneling to the top. And then eventually what will happen is once the person at the top collects enough money, they just disappear. And all of a sudden, everyone's kind of left realizing they've been scammed. So these are things to watch out for, particularly when you talk about red flags for Ponzi schemes. You should be looking at high returns with little or no risk, overly consistent returns, right? So I guess I don't do investing myself, but I'm assuming this is something that's, if you're getting, double your money every week, then obviously something's going on there. They would be unregistered investments. They would have unlicensed sellers. They'd be very secretive and complex strategies. There would always be issues with their paperwork, and there would be difficulty receiving payments. So one thing that's um, been in the news lately is looking at for potential scams using virtual currency. All right. And so even in this little yellow bullet, I'll leave that. You can pause it and read it if you want to, but it talks about a lawsuit where basically there was a scammer who claimed to be investing in Bitcoin, and it turned out to be basically a Ponzi scheme. So you can see the bolded statement here. In particular, individuals selling investments are typically subject to federal or state licensing requirements. So if you're not seeing those licenses, or you're not, that's kind of a red flag as well, right? If they're not able to produce those things. So moral of the story, watch out for Ponzi schemes. Don't get sucked into one. You can often see them on social media when people are trying to recruit. And that's not to say that every investment is like that, but you should be wary when you see people trying to recruit layers and layers and layers of investors. That's kind of a thing to watch out for, at least question. So when we look at what this looks like, here is a diagram of a Ponzi pyramid. So here you have the schemer. And the reason, by the way, it was called Ponzi is because of, I can't remember their first name, but Ponzi was the last name of the person who kind of invented this scheme in the 20s, I think it was. 1920s it is. I guess I should say that now. So what we have is at the top, we have the schemer. And so, for example, the schemer would recruit two investors and they would say, listen, give me $1,000. And then, in a certain amount of time, like let's say like next week, I'm going to give you each $2,000. So what the schemer does is they take the 2,000 off of these two people in green, but then they realize the following week they need to give each of these people back 4,000. So in order to do that, they need to recruit four new people. So the top person sends the green people out to each recruit two people. And then what you see is this repeated pattern is in order to pay the initial investors and subsequent investors, you keep needing more and more and more people to invest the $1,000. All all right? And it ends up running into something that's unsustainable. You can't get your number of investors, and all of a sudden the whole thing collapses. But by that time, this person is probably long gone, okay? But particularly what I want to look at is two things. I want to look at the growth of the people and the growth of the money required. So if we were to set up, let's just kind of do like a rough sketch of a table here. So if we were to do a rough sketch of a table and just break it down into, let's call it the round, and let's say number of people. And if we look at the dollar amount within that round, okay? So if we were to just kind of create a table of values here. So our rounds, let's start with, so they're calling this the first round. So let's call the 0th round would actually be the schemer themselves. So there's one person involved, and the amount of money is actually 0, right? Because that person's not going to pay anything. They're trying to steal the money off other people. When it comes to round 1, I know there's a total of 3 people, but what we're looking at is how many people are recruited in that round. Well, there's 2. And the amount of money that comes out at that point is $2,000. If we continue down the chain, you can see that in the second round, we have 4 people and there's $4,000. So on and so forth. When we look at the third round, we get to 8. We have our $8,000. When we look at our 4th round, we now have 16 people involved. And we look at our $16,000. And now my question for you is, how many people would be in the 5th round, right? And hopefully what you can see is that each time what's happening here, I mean, you can actually see it in each of these iterations, every one person has 2 lines coming from them. So what we know is happening there is that there's a doubling going on, right? And you can see that in the numbers here. You can see how 1 times 2 will give us 2. 2 times 4 will give us 2. So we're doubling each time. And that's kind of a key signature that you are in exponential, in the exponential world, basically. If you see something that is being caused by a consistent multiplication or division, then that's when you're dealing with an exponential, all right? So when we deal with like... We're over halfway to our 10,000 fundraising goal for our really promotion. H2H has raised a total of $6,000. My apologies for the announcement system. I'm just going to wait till it passes. If you signed up online but have not paid your sign-up fee, there will be a table set up in the cafeteria today at lunch where you can pay. We may probably get a lunch bell in the middle of this lesson. Remember, sign up there to pay your fee and you would like a t-shirt for the event. Stay tuned for more information about the event in the coming weeks. Thank you, Tiger. And now the entire world is up on what's happening in the school. So, all right. Like I was saying, what you're seeing here is a doubling, right? And so that's a key that, hey, we're changing by the same amount each time. We're changing by what's known as a common ratio of 2. So we are multiplying by 2 each time, all right? And so what would we expect to be in that 5th round? We'd expect 32. What would we expect to be in the 6th round? We'd expect 64, and so on and so forth, okay? And you can look at the money and do the same thing. Now, the only trick is that you kind of have to discard this 0th term, right? Because obviously 2 times 0 is not 0. So what we do have to look at is if we considered, say, the initial investment, because this would be the initial investment of 2,000, what's happening every subsequent round is that it's actually doubling as well. Okay? So this is kind of the telltale sign of an exponential function. Now, the general form of an exponential function, and I'll show you how this works. We're going to jump over to Desmos. The general form of an exponential function is y equals, and we're going to keep it very simplistic, a times b to the power of x. Now, when you're talking about looking at the function itself, and this is the simplest form, all right? So if you're aware of the mathematics of transformations and stuff like that, you're looking at this and you're thinking it's a little too simple. And for the scope of this video, I'm going to keep it at just these pieces right here. But rest assured, if you're aware of, say, transformations and different things like that, yeah, you can put parameters in to affect those things as well. But keeping it simple and looking at this function, this will be our base exponential function. So there are a few things to consider, right? Number one, notice how the variable is in the exponent. And that's different from something like a polynomial where the variable is raised to an exponent, okay? So we're actually switching the roles here. There is an exponential term. There is a base and exponent within the function, but the variable is taking that exponent role, okay? So let's add some sliders for these things. Now, I want to show you a couple of key things. What you're looking at right now is a horizontal line. And the reason you're looking at a horizontal line is for a couple of things. Number one, the b value is 1, all right? So if you think about what happens if I let this value be 1, then I have 1 to the x. Now, x can be any real number at once, all right? But if you let that b value become 1, it's never going to change because 1 raised to any power will always give you back 1. So one of the rules we're going to look at here in terms of exponentials is that b is not allowed to be 1. The other thing is that look what happens if I let b be 0. Okay, I get some really wacky stuff because of what happens if x becomes negative, it produces a division by 0. So the other thing we're going to have to recognize is that b for us is never going to be 0. Okay? What happens if I put b into negative values? Okay, so if I put b into negative values, you'll see that I don't get a function. There's a very good reason for that. If you were to consider what happens if we take something like negative 2 and we raise it to the power of 1, negative 2 to the power of 1 is negative 2. If we raise negative 2 to the power of 2, it's positive 4. And so what you'll end up getting is this oscillation back and forth between positive and negative powers of 2. And so that is not an exponential function as well. So for us, we're looking at a very specific set of b values today. We're looking for b values that are between, basically between 0 or 1 or greater than 1. Any of those b values will work, okay? So b values that are between 0 to basically infinity, right? For the sake of our slider, I'm just going to put it as, it doesn't need to be big because it'll get very big quick. I'm going to put it from 0 to 5. But again, it could go from 0 to infinity as long as it doesn't hold the value of 1, which you can see right now. So what happens when I change b? When I change b, what I'm effectively changing is the doubling of the Ponzi scheme. So if I look back at that Ponzi scheme, what we had was a b value of 2. Our values were getting doubled each time. So here is an exponential function with a common ratio of 2. Watch what happens if I take that common ratio and I make it 4. Now, maybe it would be better if I put these side by side, but check this out. Here's 2 to the x. So which of these two things is growing faster? The black thing or the blue thing? Hopefully you can agree with me that it's the blue thing, right? Because the blue thing is quadrupling every time. That's what this b value is talking about. This b value is talking about that common ratio, the multiplier, right? Now, I mentioned before that you can have values between 0 and 1. And so watch what happens if I take that value of 4 and I make it 1/4. Well, all of a sudden it's flipped over to the other side. And what you're seeing is that as we move from left to right, the curve is actually getting smaller. So there's where we're going to get our exponential decay. If the b value is bigger than 1, it's going to give us exponential growth. If the b value is between 0 and 1, it's going to generate exponential decay. Now, the other thing we want to look at, so I'm going to get rid of this. I'll put our slider back in for b. We don't want b to be 1. So let's stick with our Ponzi numbers for a second here, all right? Let's say that it's doubling. So here we go. There's our doubling curve, okay? And we don't need this one as well anymore. The question then becomes, what is the A value's role, all right? So what A does, if we were to let A change, is it changes the value when X is 0. This is also referred to as our initial value. So if I was to stop it right there at 9.44, and I was to look at our y-intercept, I get 9.44. So speaking graphically, there's our bell. Speaking graphically, A is the y-intercept. The reason why that makes sense is if someone was to put in 0 for X, B raised to the power of 0 would give us back 1. So this entire term would become 1. And then you would have 1 times A. And so A will always be the y-intercept of your exponential graph. In terms of word problems and contexts, it's the initial value. So to give you an example, when we talked about the money in that Ponzi scheme, we talked about the initial investment being $2,000. So if I was to make this 2,000, now granted my window doesn't look very great anymore, right? So let me go in here for a second and we'll change our x-axis to be from, let's say, -2, and we're only going to need to go as far as, like, we did 5, I think we did 5 rounds on our table. And then our y-axis, I'm going to bring it up to from 1,000, and we'll get up to 20,000. Okay, then you can see this is the amount of money involved at each round of that scheme. All right, and you can see that in the initial round, right, or the initial investment, it was $2,000, and then every time it doubled. So if I could get this to land on 1, you would see that the total is going to go to 4,000. Okay, and then 8,000, and so on and so forth. So when it comes to exponential functions, here's our kind of couple of key things. The general form is a times b to the x. The b value is the common ratio. It is the multiplier, right? Now, for the record, I know I mentioned division before. Well, multiplying by a proper fraction is the same as division. So for example, if I'm multiplying by 1/2, then really I'm dividing by 2, or vice versa, however you want to think about it. But the point is, if b is bigger than 1, you're going to get growth. If b is in between 0 and 1, you're going to get decay. Now, your a value also plays a role with that, because if your a value is negative, it will cause a reflection and can also generate a decay curve. So I'll leave that kind of for you to look at and play around with. But the big thing I want you to take is that a is your initial value, and graphically what it represents is your y-intercept. So if we leave our Ponzi scheme out of it for a second, and we just consider an exponential function, let's say y equals 3 times 2 to the x, and I bring our window back to something that's more reasonable for this scenario. So let's just start with -10 to +10 on our y and see if we can capture this thing. Okay, so that looks a fair bit better, right? What I want you to notice is the characteristics of the graph. Now, in a previous talk about polynomials, we had mentioned a few different things. First things first, does it have a y-intercept? And the answer is yes. Can we see the y-intercept? Yeah, it's going to be 0 and 3. We know that because we know our a value. Okay? Second of all, does it have any x-intercepts? And the answer is actually no. Although it gets infinitesimally close, or very, 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 very close to 0, it will never actually touch 0. And so the line y equals 0 in this curve is known as a horizontal asymptote, okay? Which is a line that a graph approaches but never reaches. Now, you can actually cross a horizontal asymptote, so I have to add that kind of disclaimer in there. But for our purposes with exponentials, this is a line that this graph will get very, very close to, infinitesimally small difference between the two, but it will never actually touch the graph. So this is not going to have any x-intercepts. And until you start working with transformations, that's going to be kind of the go-to for you. So any graph of this form is not going to have an x-intercept. And that also is the same for if we were to make this a decay curve, right? It's the same idea. It gets infinitesimally close. I know you're looking at that and saying, it's touching it. Well, trust me, it's not, and you can algebraically show it, okay? So yes to y-intercept, no to x-intercepts. Has a horizontal asymptote at y equals 0, right? The other things we cared about were end behavior. Well, if it's a growth curve, it goes from Q2 to Q1. If it's a decay curve, it goes from Q2 to Q1, right? Now, those will change if you have negative A values, right? So if we made that a -3, we can get this thing to go from Q3 to Q4. But we're actually going to deal with that a little bit different within the courses that we teach here in Nova Scotia. We're going to talk about logarithms. But for anyone who's going on to pre-calculus or calculus topics, or you deal with transformations, you can cause different end behavior. But I guess if you wanted to make this akin to polynomials, you would say that this is behaving like an even degree polynomial. It's staying on the same side of the plane relative to the x-axis. It's either staying on the top or it's staying on the bottom, okay? So for us, for the most part, it's gonna go from 2 to 1, yeah, and that's just the way it is. Now, any turning points? There are technically no turning points within this curve, all right? When it comes to the domain, x is allowed to be any real number. When it comes to the range, y obviously in this case has to be greater than 0. And notice that there's no equal to on that inequality. It's a strong inequality. So this is greater than 0. Okay? So hopefully you have a better understanding of like how exponential growth works with also a real world context. And hopefully I've educated you a little bit to stay away from Ponzi schemes. But on top of that, also with exponential equations, you should be taking away from this that the A value will give you your y-intercept or your initial value. The B value is your common ratio, which you can think of that as your common multiplier, right? They will have a horizontal asymptote of y equals 0 when they're in this form, and so they don't have any x-intercepts. They will have a y-intercept, and it's going to be at whatever the value of A is on the y-axis. They have no turning points, and their end behavior starts and finishes on the same side of the plane. So hopefully you feel comfortable with what exponential growth looks like, what its graphs look like, and how it relates to its equation.